this spectra that's linked with the diatomic molecule. And when we have a diatomic molecule, we have two atoms, and we assume that these two atoms are at some equilibrium distance with respect to each other. And now talking about this dual, I mean, uh, this molecule which has two atoms in it, which is the simplest with respect to other molecules, we can have we can have we can have two types of motions that can be uh, that can be that can be considered. The very first thing is that this molecule as a whole can rotate, and it can rotate, and the rotation can be along the axis of the two atoms, and the rotation can be along the axis that's perpendicular to the separation between the two atoms. So this rotation that we're talking about here is, this rotation will give rise to, uh, it can interact with the electromagnetic radiation depending on the molecule under consideration. If the molecule has the permanent electric dipole moment, then certainly the electromagnetic radiation will interact with it, and we will have the absorption spectra, and we will have the emission spectra. But at the same time, if the net dipole moment of the molecule, I mean, in case of hydrogen, hydrogen molecule, nitrogen molecule, we will not be able to see this what we call as a rotational spectra, because because this kind of diatomic molecule does not have the electric dipole moment, and so electromagnetic interaction is not going to interact with this molecule. But when we have a diatomic molecule like hydrogen chloride, where we have the net electric dipole of this molecule, we will certainly have the rotational spectra. Now, depending on what kind of assumptions are taken in discussing the rotational spectra of this molecule. Now, at the same time, this molecule can have vibrational spectra. I mean, when we talk about the vibrational spectra, what we have is, if we have a diatomic molecule, we have the nuclei of the two atoms, and we have the electron clouds. So there are different interactions involved in this molecule. We can have the repulsive forces between the nuclei of the molecule, and we can have the repulsive forces between the electron cloud of the two atoms that are under consideration. And at the same time, we will have the attractive force between the nuclei and the electron cloud. So what we will have here is that we will have certain considerations, and these considerations will be taken care of in discussing the. In this video, I'll be talking about rotational spectra, and what we understand till now is that uh, rotational energy is quantized along with all other forms of molecular energy. I mean, all other forms of molecular energy uh, is quantized. What does it mean? It means that a molecule cannot have any arbitrary energy. Arbitrary energy. And it cannot have any arbitrary amount of rotational energy. What it means is that any arbitrary value of angular momentum, but its energy is limited to some definite values. I mean, some particular values depending on the shape and size of the molecule. Shape and size of the molecule. Now, the permitted energy values, what we call them as, rotational energy levels. Rotational energy levels. And these rotational energy levels, in principle, can be calculated for any molecule by solving Schrodinger's equation. So, these quantized values of energy can be calculated using Schrödinger's equation for the system that's represented by that molecule. Now, for simple molecules, the mathematics that's involved is simple and straightforward. And while for complicated systems, it's probably impossible without some gross approximations that can be used to obtain some valuable solution. So what is important here is that we are not concerned ourselves unduly with this. However, being content merely to accept the result of existing solution and to point out where reasonable approximations may lead. So here, what we will start with is we will take on a diatomic molecule. A diatomic molecule. So hydrogen atom in its ground state, hydrogen molecule, I'm sorry, in its ground state is the best example that we will start with. So what we have is we have two atoms, and if I choose one atom having mass m1 and another atom having mass m2. Now, I'm not choosing a hydrogen molecule. I'm taking just into consideration a molecule having two atoms involved in it, and with masses m1 and m2. And assuming that these two masses are held together by a rigid bar, by a strong bond, we can say, for the sake of argument, and such that this length of this bond, is, say, I choose a point as R1 and another as R2. So assuming this to be C, so this R naught will be R1 plus R2. Now, what's happening over here is that this molecule rotates. It rotates from end to end about this point, the point C that I have mentioned here in the diagram. And the center of gravity, this C is a representative of the center of gravity. Now, this is defined by, we can define it in terms of a moment or a balancing equation. So we can write down this balancing equation as M1 R1 is equal to M2 R2. So the choice is clear here. We have a diatomic molecule, and the mass of each atom that's involved in this molecule is M1 and M2. They are separated by a separation of R naught, and this R naught is the bond length in between the centers of two atoms. Now, writing down the moment of inertia about this axis, this axis as C. So the symbol for moment of inertia is I. So that will be m1r1 square plus m2r2 square. So we can move on because we have this equation, so we can use this equation, and what we can write here is m2 r2 and r1 plus m1 r1 and r2, and this can be written as, so we can have r1 and r2 out, so what will be inside is m1 plus m2. And if we go back to the equation, this r naught is equal to R1 plus R2. So we can make the choice here, and we can write for R2 equal to R0 minus R1, and vice versa. So we can have those substitutions. So when we'll make these substitutions in this equation, we will be able to obtain I or R1. This R1 it will come in terms of R0 is M2 by M1 plus M2 R0. And for R2, we will have M1 R0 by M1 plus M2. So these two equations will give us a value of R1 and R2. Now, what we can do is we can use the we can replace R2 and R1 in this given equation. So on replacing these two terms that are involved in this equation, what we obtain is we will obtain moment of inertia as m1 m2 by m1 plus m2 times r naught square, and we can write down this as mu r naught square, where this mu uh, is called reduced mass. So this mu is the measure of reduced mass, and this mu is certainly, this is m1 m2 by m1 plus m2, and and this equation gives us the definition of moment of inertia, and in sincere terms, I mean in terms of atomic masses, and the bond length between the two masses. So we have two atoms, and we have a bond length of r naught. Their masses are m1 and m2. So the rotation of this molecule about its center of gravity, we measure the moment of inertia for this molecule. And uh, by making use of Schrodinger's equation, what we can show here is that these rotational energy levels that are allowed to this rigid rotator, or I may call it a rigid diatomic molecule, these energies are given by Ej equals h square by 8 pi square I j times j plus 1. So where this j is, it is 0, 1, 2, and so on and so forth. So in this equation, what we have, this h is a Planck's constant, and this I is the moment of inertia. So either we can talk about the moment of inertia IB, or IC. I mean, since both both are equal, I mean the quantity j that we have here, uh, this j can take the integral values, and the values it can take is from 0 onwards, adding 1 every time, and this is what is called as a rotational quantum number. Rotational quantum number. So its restrictions to the integral values, they arise directly out of the solution to the Schrodinger's equation, as the solution always come in the form of these quantum numbers. Now for diatomic molecule, we have J, which is an automatic consequence of the solution of Schrodinger's wave equation. And proceeding from here, so what it reflects basically is that that this j cannot have any arbitrary value. The energy cannot have any arbitrary value. There are restrictions, and these restrictions are effectively, they effectively allow only certain discrete rotational energies, and that's quite evident from this equation. So what is that equation? Is that this Ej is, it is h square by 8 pi square I j times j plus 1. Now this j should not be confused here in molecular physics with the j that we have in atomic physics, where j is a representative of total angular momentum of an electron around the nucleus. Now here, this is the rotational quantum number, so this thing should be borne in mind. So what we see here is that these energies, we have allowed energies, and these allowed energies can be written in terms of joules. And what we are interested here we are interested in the difference of energy. We are interested in difference of energies. or more precisely, we want the corresponding frequency range. We want things in terms of wave number that we have already discussed, of the radiation that is emitted or absorbed uh, as a consequence of change in energy between the two levels. Now, in rotational energy spectra, what we have is basically they are usually discussed in terms of wave numbers, and so it's always useful to consider these energies in these terms. So if I have to write down that energy, say that is Ej, so all I have to do is to divide this Ej by Hc. So this Ej is nothing but the wave number. So what we'll have here is we'll have h by 8 pi square I j times j plus 1, now centimeter inverse. So we can check dimensionality of this equation, and the things that finally we'll obtain is in terms of centimeter into inverse. And what we are actually dividing this energy by a constant, the product of two constants. So this wave number is again an indicative of the energy of the particular state of this molecule. And the symbols have all their usual meanings as we understand them. And we can boil down this Ej as B times J times J plus 1 and centimeter inverse. So this J, which is the total rotational quantum number, that is 0, 1, 2, and so on and so forth. So this B that we have here, this B is called rotational constant. It's called rotational constant. And we have its value, and its value is what? It is B is h by 8 pi square I centimeter inverse. So what we have done here is that we might equally well have used this constant, and what am I trying to tell here is that we can draw the energy levels for this rotational spectra of this diatomic molecule. So if we have to do that, we can do that for the J's that we have. We'll have a state we'll have a state 0, then we'll have a state 2b. We'll have, for J equal to 3, we'll have 6b, then we'll have 12b, and then we'll have 30b, and then we'll have 42b. So it's quite evident from this figure that for J equal to 0, what we have is we have zero energy. So we have zero. We have zero for the energy here, and we would say that the molecule is not rotating at all for this state. I mean, for J equal to 1, yeah, this is my J equal to 1, the rotational energy is 2b, and a rotating molecule then has its lowest angular momentum, and we can say, and we can still calculate this Ej with increasing the value of J equals to 2, J equals to 3, J equals to 4, and so on and so forth. So in principle, there is no limit to this rotational energy the molecule may have, and in reality, I mean, of course, there comes a point at which the centrifugal force of the rapidly rotating diatomic molecule is greater than the strength of the bond that we have between these two atoms, and the molecule is disrupted in that case. But this point is not to come up or to go somewhere at normal temperatures. So what is important now here is that we consider the difference in the levels in order to discuss the spectrum. Now, if we imagine the molecule to be in J equal to 0 state, the ground rotational state in which no rotation occurs, we can let incident radiation be absorbed to raise it to J equal to 1 state. And plainly, the energy absorbed
for these two states will be, if I take on Ej equal to 1 minus Ej equal to 0, that's going to give us 2b minus 0. So that's going to give us 2b centimeter inverse. And from this we can write down the wave number. And at the same time, if I have to translate it in some other words, an absorption line will appear at this 2b centimeter inverse. Now, if now the molecule is raised from, say, J equal to 1 state to J equal to 2 state by the absorption of some more energy, we can immediately see that this Ej equals 1 minus uh, Ej equals 2 is going to give us 6b minus 2b. That's going to be 4b centimeter inverse. So in general, if we have to raise the molecule from a state J, some J, to a state J plus 1, we can generalize it, and we can write down it in terms of the wave, in terms of the wave number. So nu bar J to a state of J plus 1 is going to give us B times J plus 1 times J plus 2 minus B J times J plus 1. So we can solve this. We can have B outside, and what will be inside is J square plus, so we'll have 2J, 1J, that will give us 3J, and plus 2, and then minus J square will come here, so minus 1. And we can have some cancellations, and here it should be J square. So this J square and J square will go, and this is J times 1, so this is J. Okay, so what we can do here is we can have this this term will be 2b times J plus 1. So in order to raise the molecule from the state J to state J plus 1, we have the wave number 2b times J plus 1. And we can have those transitions, and we can put those transitions, and we will have the spectral lines. If I have to show them, so this is my 1, 2, and 3, 4, and 5. So this will be my 0 state, this will be my 2b state, this will be 4b, and this will be the line for 6b, and this will be the line for 8b, and then 10b, and so on and so forth. Now we have a stepwise raising of the rotational energy, and this raising results in an absorption spectrum. So you have the raising of energy, so consisting of the lines 2b, 4b, 6b centimeter inverse. This whole thing is in terms of wave numbers. So at the same time, the similar lowering would result in the identical emission. So the state lowering from 10b to 8b, 8b to 6b is going to give us all those respective energies that were absorbed when the molecule was raised from lower energy states to the higher energy states. Now, again, in talking about this picture, we have made the assumption that the transition can occur only from particular level only to its immediate neighbor. So either this transition can be one above it, or this transition can be this transition can occur some particular levels only to its immediate neighbor. So it can be either above, or it can be below. At the same time, now for instance, what we consider the consequence of the transition that we have, say J equal to 0 to J equal to 2 to J equal to 4. I mean, in fact, I'd rather some sophisticated application of the Schrodinger equation shows that for this molecule, we need to consider only those transitions in which this J changes by a unit. All other transitions being spectroscopically forbidden. and such a result of what's generally known as selection rule. And this selection rule can be formulated, and the selection rule here is that this delta G can change by only plus minus 1 for this diatomic molecule. So this equation that we have here, it gives us the whole spectrum to be expected for such a molecule, which is a diatomic molecule. And now, at the same time, only if the molecule is asymmetric, uh, will this spectrum be observed. Since if it is homonuclear, uh, there will be no dipole component change during the rotation, and hence no interaction with the radiation. So we can say the molecule, like hydrogen chloride, or carbon monoxide, these kinds of molecules, they will show a rotational spectrum. And on the other hand, if we have nitrogen molecule or oxygen molecule, they will not show us the rotational spectrum. So what is important here is that the rotation about the bond axis was uh, uh, was about the bond axis was rejected. And we can now see that there are two reasons for this. I mean, firstly, the moment of inertia is very small about the bond, so we see that the energy level is raised by uh,